Hello, this video will introduce a deep learning-based RFF identification system for LoRa, and I'll demonstrate how to operate this system with a brief test. Firstly, let me show the setup of the system. In terms of the hardware, I use 10 low-power boards as the transmitters to send the LoRa packets, and I use RTL SDR to receive the signal and convert the analog signal to digital signal. Jetson TX2 is an embedded board that is used to process IQ samples and perform convolutional neural network training for classification and identification. As for software, the transmitters are controlled by using MicroPython. The graphical user interface and the signal processing are programmed by using Python. The CNN training is implemented in Keras, which is a Python deep learning API. And Jetson TX2 is remotely controlled by using Mobile X2. Then here is the structure of the RFFI system. It has three stages: data collection, classification, and inference. Firstly, the system should collect 500 differential spectrograms for each low-power board, respectively. Each device are labeled with an index from 0 to 9. Then they are fed into the neural network for training. After the training, the RFF feature will be stored in a CNN model. The system can identify the trained low-power board without index according to the model. Each step will be shown in detail in the following slides. I designed a GUI to demonstrate the procedures of the complete RFFI system. It can be divided into 8 regions. The headline shows the title and the logo of the University of Liverpool. The setup region configures the transmitter and SDR. Below it, there are 2 button actions that can trigger data collection and CNN training. The right region is to display the figures in real time, including the LoRa packet in time domain, the spectrogram of the packet, and the result of CNN training. The inference region provides the identification function, and the result will be shown in this region. Next to it, there are several statistical results that can help to evaluate the performance of the system. The message region can display the ongoing process in text form. The button region shows the current status of the system. Next, I'll show each step in detail. With the signal generation of a transmitter, the first step is data collection. Here is the configuration of SDR. It can be shown that the transmitter is the number 1 low-power, the receiver is RTL SDR, the sampling rate is 1 MHz, and each device needs to collect 1000 packets. Then click on the button. The system will begin to collect LoRa packets. While the system is collecting packets, the graph region displays the time domain and spectrogram of the captured packets in real time. Each packet should be transformed into a spectrogram before CNN training. Meanwhile, the message region shows the current process, including the number of collected packets, SNR, and CFO. Each packet requires CFO composition, which is caused by the frequency difference between the oscillators of the transmitter and the receiver. After collecting 1000 spectrograms, change another transmitter to send LoRa signal and repeat the same procedures until each device has collected 1000 spectrograms. The next step is to feed the collected spectrograms into the convolutional neural network. Before training, several parameters should be set first, such as learning rate, batch size, epoch, and so on. Then the CNN training will begin. It can be shown that the Jetson TX2 developer kit uses GPU for CNN training. A powerful GPU can accelerate the training process efficiently. Here is the plot of the loss and accuracy variation over epoch. After the training, a confusion matrix will show the result of classification in detail. The result shows the training accuracy can reach 98.5% and the training time is 5.02 minutes. Finally, The trained CNN model is stored in Jetson Text2 Developer Kit. The final step is identification. It is also the main function of the RFFI system. Click on the Load module and choose a trained CNN model for inference. Then randomly choose a transmitter to generate LoRa signal. In this test, the index is the number 1. Next, click on the button. It can be shown that the system can successfully identify the device index 1. Then change another transmitter and inference again. The system can still output a correct index. Finally, move device 1 to a different position and continue to identify it. The system can still recognize the device 1. This means that the system is robust against the changes in the wireless channel. This is the entire procedure of the RFFI system. Thanks for watching.